in phase behavior. I'm going to show you the experiment so you can understand what happens through our experiment. Well, we have here a syringe pump where we're using the syringe pump on a very small flow rate, very low flow rate, where we can pump through this micromodel. A micromodel, it's a model that is etched in glass. It's a 2D model. There you have a picture in our very first class of this first lecture, this video lecture, in the second day lecture, and you can take a look back at that if you want, right? And you see the flow rate that we were using and the velocity that we were actually using in that. Although the velocity were very small, they're not small at all when you're thinking of speeds of groundwater in a field. We're thinking of doing that in our experiment. That was low enough for us, and although that, we still had a magnitude lower than the critical capillary number that would mimic the field situation. Okay? So what we had is we're actually creating residuals and then injecting ethanol. First we fill with gasoline, then we flush that with water to develop gasoline residuals. This is the water was the wetting fluid in this situation here, and we end up creating gasoline residuals. A second model, we had a glass bead model, as we see here, same situation, but this is in a much larger experiment. We had two plates of glass, get one plate of glass, and then you put glasses, like a window glass that you have on your home, right? You get a plate of this size, that's the actual size of the experiment, and then you put it horizontally, and you put a tiny band of glass on the sides, and you fill it with maybe 3 layers of glass beads, and you put another, just enough to cover the surface, and then you put the other glass on top of it, and then you go to the oven and you melt it together, and you develop a quasi 2D model that you can see through. So the idea was developing a model where we could actually videotape the flushing before we went to the field. That's quite neat. I had a lot of fun preparing that, actually. Well, when I see today. So this is an experiment that was prepared by Juliana Freitas. She was also a PhD from Waterloo. Today she works at UNESP, São Paulo, Brazil. And this is a very neat experiment. Thanks to Juliana, we have this that we can show you how it works. Please pay good attention at that video, because you will actually see what happens in a field situation. Take a look. First, what we have here, this is an aquarium, plexiglass aquarium here, you see? Well, we take our 2D model, and it's open at the one side here, it's open at the top here. This is glass bead, it's not sand, so it's this thick. And what we do is completely dry. So Juliana inserted the model into the aquarium, and she inserted the model in the aquarium. You had water at this level at the aquarium. Well, by capillary forces, you develop a capillary fringe here. This region is water that invaded the pores by capillarity alone, right? This is the capillary fringe that formed. Since the model is very homogeneous, what we see here, it's a very homogeneous capillary fringe. Although it's homogeneous, you still see that you have differences here. Some points you reach it higher, some other lower. So this was considered the top of capillary fringe. This was drawn the side of the aquarium so we could take a good look, right? And of course you don't see here the water table, because the water table in the porous medium, it doesn't exist, right? It only exists in the well. so if you look at the back of the aquarium here, at the back of the aquarium you can actually see the water table because it was inserted, and you have a larger aquarium, you can see the top of the capillary fringe. So Juliana was kind enough to draw the position of the water table. As we release this movie to you, you will see the point where gasoline was injected here. Gasoline is going to come down through the unsaturated zone, is going to reach the top of the capillary fringe, and we'll see what happened. And I will discuss with you in detail the development of that. So just roll the movie. Wow, that was nice. Again. Well, I'm going to do that again. So take a close look. What I want you to see now is the exact moment where the gasoline touches the top of the capillary fringe, and see what happens. Boom. Immediately after the gasoline reached the top of the capillary fringe went down. That was immediately after. The first thing that might come to your mind is that, well, as the gasoline, you have a head of gasoline that's coming from the top. It reaches there and it pushes the gasoline, the water downwards. As it pushes it downwards, it changes the capillarity and it moves. Well, that would be the case, but it's not the main thing that happens right at the moment when it touches the water. When it touches the water, the gasoline free phase that is coming down, actually what you had was previously you had water, air. This is the interfacial tension that is acting. When the gasoline displaces air and it touches directly the water, now you have an interfacial tension between water, gasoline, which is a different interfacial tension, much lower. And the capillarity that would develop should your porous media be covered or filled with gasoline is different than when it's filled with air. So right after it touches, the capillarity changes and the water table goes down. Take a look, the capillary fringe goes down. Look at that. It's going down. It's going down. Why? Because you have the gasoline spreading on top of the capillary fringe. We didn't have, as you see in this here, we didn't have enough gasoline to actually change the water table. The whole phase of gasoline spill here, it's all above the water table. We have here lateral spreading of the gasoline, and it's all remaining on top of the capillary fringe, right? See, water table remains here, and the whole distribution of product in free phase. This is free phase because it was flowing laterally, and if it flows, it is free phase, right? So it flows here. We have a development of free phase only on top of the capillary fringe. That is quite nice. Oh, again, first thing, changing in capillary fringe. So the capillary fringe was higher, and it becomes lower, not only due to the weight of the free phase, but mostly first because of the changing in interfacial tension. And as we see here, interfacial tension changed, but still, you have capillarity, and water is still keeping the free phase above the position of the water table. This is all nice physics, and that's all you have to understand when you go to the field. Should the pores be smaller and the capillary fringe be higher, you still have a higher position of the gasoline free phase. the pores be larger and then not as high a capillary fringe, and probably it will displace everybody down, and you would have the free phase at or even below the water table due to the weight. Again, should I add more free phase here and then I develop a thicker free phase, then the weight and the hydraulic head that it develops would push the water down, and then you end up having free phase below the water table by pushing by weight that water, the water that was trapped by capillarity only. Okay? Actually not trapped, that was elevated by capillarity only. That's quite neat, and I do recommend you watch this video several times, and I'll repeat it a last time here. Thank you, I hope you enjoyed it.